Okay, so you heard that. So we are recording now. Okay, so is it okay to start?
Yep.
Okay, great. So, right. So it's a pleasure to have Benoit Claudon with us today from Université de Rennes. Benoit will be talking about numerical characterization of complex tori.
Okay, thank you, Beru. So it's my pleasure to give a talk in this ZAG seminar. No, I have to use that. Oh, sorry. Why? I'm sorry, it did not working very well. I can't, or maybe, sorry. As you see, so this is my first, I can't use the arrow.
Oh.
To switch, or maybe just, okay, so sorry, okay, so
it's working now.
I have this small pad. Sorry for the mess.
Right,
okay, so here is the plan of the talk. So I'm going to explain, so as Beru said, the characterization of quotient of complex tori. And so first I want to explain the smooth case. So it corresponds to a free action of a finite group of a complex torus. So T is this complex torus, and G is a finite group, and we assume that this G acts freely on T. So in this situation, we can consider the quotient. So of course, this is a nice manifold and smooth, and this is compact and Keller as well. So we can easily compute the Chern classes because of the functoriality, for instance, and as the Chern classes of the torus vanish, then the same happens for X. So we have the vanishing of all Chern classes, and so it's natural to ask if the reverse holds, and in this Keller situation, then it's a very nice feature of the Keller situation that we indeed have this converse. So first, if we have the vanishing of the first Chern class, then this is a consequence of the celebrated Yao theorem. If I pick any Keller metric, any Keller class, sorry, in this cohomology class, we can find a Keller metric such that the Ricci curvature of this metric is 0. So this metric is Ricci flat, and from now on, we are going to use this metric to compute Chern classes. So not only Chern classes, but Chern form. So I can compute the Chern forms of the tangent, and so it's a classical computation that if you use the Keller-Einstein condition, so the fact that the metric is Ricci flat, then we can compute this quantity, so 2nc2 minus n-1 c1 square, and we wedged against omega to the n-2, and this quantity, so up to a non-zero universal constant that depends only on the dimension. So this is the L2 norm of something. So this is not the full the full curvature tensor, sorry. There is this 0 here, so this is the traceless tensor. But here we are in the case C1 equals to 0. So in that case, so the traceless tensor and the curvature tensor coincide. So what do we get? So if C1 is 0, so this term vanish. And if I just impose that this cohomological condition, so the fact that this C2 wedge, oh sorry, there is a mistake here. This is omega to the n-2, of course. So if we have the vanishing of this this cohomological number, then we get that the full curvature tensor vanish, and so the X has to be a quotient of a torus. So it can be easily seen using, for instance, uniformization and Lieber-Bach theorem. Okay, so we see that in this context, quotient of tori, étale quotient of tori, can be detected just using vanishing of Chern number or classes. So Chern classes for the C1 and Chern number for this C2. So it's, at least to me, it seems a quite natural question to study the general case, so where the action of G is not free anymore. And in that case, we are led to consider singular spaces, of course. But in that singular setting, so there are at least 3 difficulties. So first, we have to identify a natural class of singularities. Okay, so this is a ZAG, so zoom algebraic geometry. So it's not surprising. So we will deal with KLT singularity. So as you know, so the quotient singularities are indeed KLT, and so it seems rather natural to work in this category of singularities. The second difficulty that we can identify is the notion of calorimetric in this singular setting. But good news, it was settled by Grauert in the early 60s, and so there is a very good notion of what is a Keller space. Essentially in the normal case, but that's what we need here. So, and last but not least, so what is the notion of Chern classes or Chern numbers in this singular context? And this is absolutely not obvious, because we can find several definitions or theories in the literature, and it gives you different way of defining and computing Chern classes. So it was done first by Macpherson, and then with Bohm and Fulton, and Marie-Hélène Schwartz also did some nice job in the analytic setting. So the first 2 references were in the algebraic setting, of course. Okay, so now I'm going to spend some time to explain what is this. So what notion of Chern classes we use in this talk. So it's we chose to. Oh, I said we because I forgot to mention that this is joint work with Henri Ganancia and Patrick Graff. So with my co-author, so we chose to follow a very a simple path to define Chern classes. So here is the way we used. So if you consider a torsion-free sheaf on a normal complex space, then you can always find a resolution F such that not F star E, but F star E mod torsion is locally free. So it's a combination of Hironaka and a result of Rossi. And so we fixed this resolution with this F sharp E locally free. And then, so what we define is not the Chern classes, but we define Chern classes acting on cohomology group. And so with this very basic formula, so the Chern classes act on the right cohomology space. So using the pullback to X hat, and you intersect with the corresponding Chern classes of F sharp E. Okay, so of course it can also be done for a polynomial or homogeneous polynomial in the Chern classes. In this talk, we are only concerned with the C1 square. So this is the only formula I plugged on the slide. But of course, you can, if when I say homogeneous polynomials, of course you have to think of weighted homogeneous polynomials. So such that the A has a fixed degree. So the cohomology class has a fixed degree. And here, so the formula, so you look, you can see I put the square is just above the C1. And there is a reason for that. So you will see in a minute. So we compute C1 square against A as just the C1 square on the resolution against F star of A. Okay, so of course, we have to check that this is well defined, because at the very beginning we chose a resolution F. And okay, so it's so it's well defined. It does not depend on the choice of the resolution, so that's good news. And so the second properties is that these channel classes, they are defined just as linear form on the cohomology, and so using duality, so we see that these are just homology classes and not cohomology classes. So in particular, there is no reason to be able to wedge channel classes. And that's one of the problems. So for instance, if you assume that the C1 of E can be defined as a cohomology class, for instance, if the determinant of E is Q Cartier, so sometimes it happens. So you can consider C1 square of this of these classes. So it lives in H4, upper 4. So you can see in H2n minus 4. But in general, you will see that the C1 square with the square on the left of E is not the C1 square with the square on the right of E. And so the example is very simple. So you just have to, you pick a point in a surface and you look at E, the ideal sheaf of this point. And of course, to be able to compute the channel classes as we define in the beginning of this talk, so it's enough to blow up the point, and so we get the pullback of this E is nothing but the line bundle associated with minus E, where E is the exceptional curve. And so easy computation, so it shows that the C1 of E is 0, but the C1 square is not. So it's just e to the square, where E is the exceptional curve. So we see that we have to be very careful, even in the smooth case. But the point is that we consider torsion-free sheaf and not locally free sheaf. But hopefully, so there are when we have good condition on the codimension of the singular set, then we can hope for some compatibility. So I plug one, I displayed one of them in this slide. So for instance, if E is locally free in codimension 2, okay, so that's not the case above, of course. And if the determinant is Q Cartier and X smooth in codimension 2, then in that case we can permute the case, so we can put it on the left or on the right of the E. Okay. So this was a definition for channel classes of sheaves, but we can also define channel classes of space. And here is so I named it proposition definition. So if you start with a normal complex space, and you assume that this space admits a resolution that it's minimal in codimension 2. So there is a codimension-free set in X, such that away from this set, the resolution is minimal. Then in that case, so we can, using the same trick, so we can define C2 of X acting against a class A. So A is in H2n minus 4, just as the C2 of Y wedge the the pullback of A. And so it's one of the magic that it does not depend of this resolution F, but it's much harder than in a sheaf case. So it was proven by Graf and Kirchner in a previous paper. But okay, so you see there is this assumption that X admits a resolution that is minimal in codimension 2, and so it does not apply to any space. But luckily for us, in the case of KLT singularities, it applies, and so it comes from the fact that away from a codimension-free subset of X, KLT singularities are just quotient and surface quotient singularities. So this is a nice, very nice result for the local structure of KLT singularities in codimension 2. So they are given by surface singularities, quotient surface singularities. And so in particular, the minimal, for instance, the minimal resolution of this X, so minimal in the sense of Collar, for instance, so it will be minimal in codimension 2. Sorry, the functorial resolution. The functorial resolution of X will be minimal in codimension 2. So we can compute the C2 of X when X is KLT. But of course, there is still a problem of compatibility of two definitions, to a priori different definition. So we can compute the C2 of X and also the C2 of the tangent sheaf of X. In the smooth case, they coincide by definition. But in this singular situation, so if X is smooth in codimension 2, then we have the compatibility of both definitions. But as always, we have to be very careful, and so there is this basic example of the Kummer surface, but very instructive, always very instructive. So you pick a torus and a surface, and then you mod out by plus or minus 1. And so the quotient X has 16 singular points, just E1, sorry, A1 singular points, and then the minimal resolution just obtained by blowing up all of this the singular points. So it's a K-free surface, and the exceptional divisor is the union of 16 minus 2 curves. And in this very basic example, we can compute, and on this resolution, the pullback of the T of Tx is the logarithmic tangent bundle on X hat, logarithmic with respect to E, of course. And so with this at n, we can compute the various Chern number or classes in that case. So the C2, the birational C2. So sometimes this quantity is called the birational C2. So this is nothing but the C2 of X hat. So this is 24. But we compute the C2 of Tx by its very definition, it's the C2 of F star Tx. And we compute using the exact sequence you want, and you get that this C2 is minus 8. So it's not equal to the C2 of the space. And last computation. So you see that this example gives you also an example where the C1 square is not equal to the C1 square. So if the C1 of Tx is 0, but the C1 square of Tx, so computed on the minimal resolution, it's nothing but the E square, where E is the exceptional divisor. And so this is 16 times minus 2, so minus 32. Okay, so we see that this birational C2, okay, it's in some sense, it's useful essentially in this situation where the X is smooth in codimension 2. Okay, so now I come to the statement. So as I said, I just realized that I forgot this assumption that X is smooth in codimension 2. So in the algebraic setting, it was first this kind of numerical characterization of complex tori were investigated by Greb, Québecus, and Peternel, and they proved that if X is a projective KLT variety with C1 equals to 0 or Kx numerically 0, and assume that this birational C2 is 0 against an Ampere class. And as I said, I forgot to mention that X is smooth in codimension 2. Then X is the quotient of A by G, where A is an abelian variety and G a finite group acting freely in codimension 2. Okay, so of course the fact that the action is free in codimension 2 is just the incarnation of the smoothness of X. So with Henri and Patrick, so we formally, so you see, we get exactly the same result, but in the Keller setting. So X normal compact Keller, smooth in codimension 2. C1 equals to 0 and C2, this birational C2 is 0 against the Keller class. Then X is a quotient of a torus. So I just want to give a very rough idea of how goes the proof in the algebraic setting, just to show that we cannot follow this way to tackle the analytic one. So in the algebraic setting, the first step is to consider a smooth surface that is a complete intersection. So the fact that this complete intersection H1 intersected with Hn-2, the fact that this surface is smooth is a translation of the smoothness of codimension 2 of X, and so this surface is also contained in the regular part of X. And the trick is to consider the restriction of the tangent sheaf of X to S. And if the HI are chosen sufficiently general, then this E will remain semi-stable on S. And so this is a vector bundle, a rank n vector bundle that is semi-stable, and it precisely have vanishing chain classes C1 and C2. So according to the Simpson correspondence, this E is flat and associated with some linear representation of the pi1 of S. And the step then is to use this singular version of the Lefschetz theorem. So the pi1 of S can be identified with the pi1 of X reg, sorry, the regular locus of X. And so this representation, it can be thought to live on X reg. And so there is a flat bundle that corresponds to this representation on the whole of X reg. And so the main input is the use of this maximally quasi-étal cover introduced by Greb, Québecus, and Peternel. So since X has KLT singularities, so up to replace X with a quasi-étal cover, then we can assume that this representation with value in GLN, it factors through pi1 of X and not just pi1 of X reg. And so this is very powerful, since now it shows that the tangent itself is completely flat on X. So by Bertini type argument, so you easily see that this Tx coincide with the flat bundle associated with the representation. And so in particular, it is locally free. And we know, so from previous work of Greb, Kovac, Quebecus, and Peternel, that if X is KLT and the tangent sheaf is locally free, then X is smooth. So this is the so-called solution of the Zariski-Lippmann conjecture in that setting of KLT spaces. Okay, so you see that when we start with X compact Keller in the analytic settings, sorry, we are stuck, and we have to find another path, and maybe a naive ID. Okay, so what about the possibility of finding a deformation of X? So a nice deformation, so locally trivial, defined over a smooth base. So here D is this mat BBD is just a neighborhood of 0 in some affine space. And so, and the hope was to be able to deform X as a projective variety. Okay, so this is already something. Okay, no, this is true in this Ricci flat case, but not so easy. And we are going to use that at the very end of the argument. But in some sense, it can be seen as too naive, because it's a priori it's not clear at all if the vanishing of C2 will be preserved on a Keller class. So we don't know how the Keller cone deforms in this family, and so it's not clear how to preserve this condition. And one way to guarantee that would be that the C2 is identically 0 as linear forms or as a homology class. So because in that case it would be something topological, and this kind of locally trivial family are trivial in the topological sense. Okay, so maybe it's too naive, but maybe in some case, maybe we can use that. So we will see. Okay, so I said that we have to follow some very different paths, and so the first thing is to prove some high positivity of this birational C2, and it's done through the well-known Bogomolov-Gieseker inequality. And in that case, so in the singular case, so we get the following. So if X is a normal compact Keller space, alpha a Keller class, and E, this is a reflective sheaf that is stable, or actually semi-stable is enough, but and with respect to this Keller polarization we fixed, and R is the rank of E, then we have this the essential. So formally, this is the same inequality. So the fact that this Bogomolov-Gieseker discriminant delta of E, that is nothing but 2R C2 minus R minus 1 C1 square of E against alpha to the n minus 2, that is non-negative. And so the interesting point is the study of the equality case. And in the equality case, we were able to prove that so if delta of E against alpha is 0, then delta of E against beta to the n minus 2 is 0 for any Keller class. And for instance, if X has rational singularities, so KLT, for instance, essentially it says that the Bogomolov discriminant is 0 against the H1 mark. We don't know what happens with the H2 0 and H0 2 part, but we have this vanishing for the for this large part of the H2. Okay, so maybe a nice corollary. So as I said, so this is a semi-positivity of the C2. So if X is KLT compact Keller, smooth in codimension 2, this time I didn't forget this assumption. And if the C1 is 0, then the C2 is non-negative against any Keller class. And if we have equality for one Keller class, then we have equality for any Keller class. And but the proof is, it can be seen, for instance, so since you remember in this Bogomolov-Gieseker, so I said that E is stable, so in general T is not stable, but only polystable. So first we have to replace X with a quasi-étale cover such that the Tx is split as a direct sum. So all this EI are stable with respect to alpha, and the holonomy of each summand with respect to a nice metric, so to a Ricci flat metric, the holonomy is contained in either SU or SPN, and in that case, so in particular, it gives you that the determinant is trivial, and then you use that the C2 of X can be computed using the C2 of Tx, and then it's you apply the Bogomolov-Gieseker, sorry, for each summand EI. Okay, so now we have this semi-positivity, but we still don't know how to apply it. And but we can we can use the full force of this result. So it was recently proved by Baker, Ganancia, Elaine, that the decomposition theorem holds in this singular setting. So what is the decomposition theorem? It says that if you have a compact Keller space with C1 equals to 0 and KLT singularities, then up to replace X with X with étale cover, quasi-étale cover, then we have this decomposition. And what are the pieces of the decomposition? So T is a complex torus. Each of the yi are Calabi-Yau spaces. So in particular, KYI is trivial, and we have no reflexive forms on yi except for the 0 and the top dimension. And the last piece are so-called irreducible holomorphic symplectic varieties. So they are endowed with holomorphic symplectic forms. Okay, but now how to use this decomposition. So first we can remark that since yi and zj have no h1, so when you use the Kunet decomposition of the cohomology of X, so you see that any Keller class on X can be decomposed as a sum of Keller class. So we are going to, in some sense, we are going to study separately each summand of the product. So alpha is the sum of alpha t and sum of alpha I and sum of beta j, where the forms are Keller class on the corresponding factors. And since X is smooth in codimension 2, then we can compute C2 against alpha to the n minus 2 as the C2 of Tx. And we know that Tx splits as a sum of the tangent space of the torus, etc., tangent space of the Calabi-Yau part and the tangent space of the IHS part. Of course, the part corresponding to the torus, the C2 is 0. And so at the end, when we compute this product, so we see that this is just a sum. Okay, we may have some coefficient here, but some positive coefficient, but this is just a sum of the different contribution of the C2 of each factors against the Keller class coming from this the corresponding factor. And we can use semi-positivity for this factor. So we have that C2 TYI against alpha I to the right power is non-negative, and the same for the ZJ. So if C2 of x, where alpha to the n minus 2 is 0, then we get that all these factors are satisfy the same hypothesis. So to conclude the proof, so we have to exclude the possibility that the C2 of CY Calabi-Yau space or irreducible holomorphic symplectic variety is non-zero. Is zero, sorry. Okay, so first we begin with the CY case. So the good news is that a Calabi-Yau variety with KIT singularity, it's always projective since it has no two forms. And here, if we assume that we are in this, we have this vanishing for one Keller class, we are in the equality case of the Bogomolov-Giesecker inequality, and so we can apply this equality case, and we have the vanishing for any Keller class, and in particular we can pick an ample class, since, as I said, Y is projective, and so we are exactly in the case of a GKP theorem, and so we would get that Y is a torus quotient or quotient of an abelian variety, and that's not the case. Okay, so the CY, so due to the projectivity of Y, this is easily settled in this case. But what about the last one? So the irreducible holomorphic symplectic one. So here the trick is to use the Boville-Bogomolov form. Okay, so we know that the H2 of Z, this coefficient in Q, in R, or whatever you want, this is ended up with a canonical quadratic form, so I denoted by QZ, so called the Boville-Bogomolov form. And in some sense, this Boville-Bogomolov form is the unique one that is invariant by parallel transport, okay, in deformation. So using that, it can be proved that if you consider this mapping, so alpha mapped to alpha to the 2n. Of course, here we are, the dimension is even, so now n is just the middle of the dimension. So alpha to the 2n, so this is nothing but a constant times QZ of A, sorry, to the n. So you can see that this QZ is a kind of nth root of the intersection form on Z. Okay, so this is this identity is very well known especially in the smooth case, but it's also old in this singular case. And maybe the second one is less known actually. So there are Fujiki relation for any even degree Chern classes on Z, and so it gives you the fact that C2 of Z against A to the 2n minus 2. So this is essentially QZ of A to the n minus 1. So we can express all the quantity we are interested in with respect to this quadratic form. Okay, so now we can use the vanishing of the C2. So you see that if the C2 vanish against one Keller class, so we see that QZ of A is 0, but if QZ of A is 0, then you see that the only possibility is that this mu1, this constant mu1 is 0. And so if you have the vanishing against one Keller class, then you have the vanishing against the whole H2. And you remember when we tried to implement our naive ID, so it was the things we were looking at. And now we can perform this deformation argument. So it was proven by Bakker and Lane before this. It was a first step toward this decomposition theorem that IHS variety even in so in the analytic context, they always admit algebraic approximation. So we can find such a nice family for Z. And since we have the vanishing for the whole of the H2, we can apply GKP on a projective deformation of ZT. And again, sorry, we get a contradiction because, okay, so you see we have this the fact that the nearby fiber is a torus quotient, but since the deformation is locally trivial, it shows that Z has quotient singularity itself, and so we can conclude using this new information, this new input. Okay, so in some sense, it's a little bit disappointing to use the full force of the decomposition theorem to prove this this numerical characterization, but we tried hard, and that's the only way we found. So in case you have some better idea, I'm here to listen. And so maybe just a few words to, I will be in advance. So before ending this talk, so maybe some word about the future. So to be able to treat the complete case, so it would be great to know how to deal with this orbifold second chain classes. So it was defined by Graf and Kirchner in the analytic setting, and there is also another construction that was used by Mumford and many other after that. So to define this C2 orb in the algebraic setting, and Graf and Kirchner, they also proved that what they introduced in the analytic setting coincide with the Mumford construction. So we have a very natural notion of orbifold C2, and so for instance, you see in the case of the Kummer surface, Kummer example. So I said that the birational C2 is 24. So of course, this example, this is not a counterexample to our theorem because the C2 is non-zero, but the C2 orb in that case is 0. So in some sense, it says that this orbifold C2, it better encapsulate the information of a tentative cover by a torus. So here, so it's a tentative statement. So X, so if X compact Keller, KLT singularity, and here there is no assumption on the smooth in codimension 2. So if the C1 is 0 and the C2 orb vanish against the Keller class, then X should be a torus quotient. Okay, so here the difficulty is that it's very hard to deal with this C2 orb in this analytic setting. And as I said, because we do not have this this Mumford trick to compute the C2 orb. And okay, so what is this statement? So the statement I presented today is the exact analog of GKP, and the statement that I display right now, it would be the analog, the analytic analog of result proven by Stephen Liu and Beruz. So in the algebraic setting, and alpha was also an M1 class. And maybe a last point. Okay, so maybe, so here you see that in this tentative statement, you see that the conclusion would be that X is a torus quotient and the group acts freely in codimension 1. And so what about completely general group action? So no freeness assumption. And so to be able to treat this kind of situation, then we have to add some orbifold structure, but hopefully this this C2 orb, it can also be implemented and used in this. So when the orbifold structure exists in codimension 1, so maybe it would put a final period to this story in the analytic setting. Okay, so I stop here, and sorry for being so so quick.
Great. Thank you very much, Benoit, for the talk. Okay, so this is something I have to do in vacuum, so I sometimes forget. Thank you.
Thank you, Beros.
Okay, so any questions, please? Okay, so maybe I'll warm up a little and start with asking a question myself. So this graph, Krishna, the C2 that they define,
yeah,
was there? I'm a little hazy on details. Was there some restriction on the dimension of this X when they defined this orbifold C2?
No.
So they
Actually,
define
so
orbifold.
this is just they use the trick that in codimension 2, X has quotient singularities.
Yeah.
So you can define, so you look at the orbifold locus of X. So it's a very big open set. This open set has some, you can compute the orbifold Chern class for instance, using Satake construction or something like that. So you can define a class for this guy. And the magic is since the set you removed as codimension 3, so the real dimension is at least codimension 6, and so it's exactly say that the H2n minus 4 of this open set is the same as the H2n minus 4 of the whole X.
Right. Yeah. No. I see that. But you're saying that X. So in their paper, X is not algebraic. So it's some any sort of complex analytic.
Okay. So I thought that the question was about the definition. So it's defined for any KLTX. So regarding the dimension, regardless of the dimension, and but so they proved the tentative statement. They proved it in dimension 3. Okay, so
I see. So the tentative statement was proved. Oh, okay.
Okay. So in the Graf Kirchner paper, that they proved this characterization, but only for threefold.
I see. Okay.
And they really used the full force of the classification or the description of the Albanese map of the.
So you don't. So you wouldn't. So I'm just saying that there is a definition, working definition for C2 there already. So you don't need anything.
Yes. So, but
okay.
They are able to use. Okay. In some sense, they combine this definition with the knowledge they have on X, but in the higher dimensional case, so we cannot use this kind of.
Oh, I see.
Of description. So, for instance, Patrick proved that the Albanese map of a threefold, of a compact Kähler threefold with C1 equals to 0 is isotrivial, and we don't know this. We don't have this kind of statement in.
I see.
The dimension.
Okay. Right. So that's that question. The last thing, the orbifold thing that you mentioned at the end. The algebraic one is there. I guess you're asking the analytic one. So I'm just saying that in this orbifold setting, the sort of the right C2 in exactly the setting that you're working with.
Okay.
It's already. That exists, but I'm not. The analytic one is probably.
Okay.
Yeah.
Yes. No. You say that the C2 exists in this setting.
Yeah, so the paper I
No,
have with
and
Henri.
the characterization, is it also?
No. Characterization. I mean, in the
Does it
paper
exist?
with Henri, when we proved the sort of the inequality one.
Yep.
That's you're saying that if the inequality is equality in that paper, then you have this orbital torus quotient sort of situation.
Yes. So the
right.
okay.
Right.
So the number exists. So the C1
yes,
of
the inequality. The
yeah, the
inequality
C1, the C2 of a pair. So this is well defined.
Yes.
And I guess we can use the same trick by Graf and Kirchner in the analytic setting. So you see that if you take a pair with standard coefficient, then in codimension 2 it has quotient singularities. So we can apply the same. So you look at the biggest open subset of X such that the pair is an orbifold.
Right.
And you apply the same. Okay, but this is just a formal trick that gives you some numbers, but how to deal with in the real life. So that's the point.
Yeah, I understand. Okay. Any other questions with from Benoit? Okay, if there are no further questions, let's thank the speaker Benoit again. Thank you very much for the talk, Benoit.
Thanks, Berouz, for presenting and asking.
So I'll stop recording now. I have